In this video, we're going to review some information about chemical bonding that we've learned before, and then also talk about a new concept called electronegativity that's very important to chemical bonding. So a lot of topics that we've covered previously help inform what we know about chemical bonds. And so atomic structure, electron configurations, periodic properties, all of these things influence our understanding of chemical bonding. And we know that chemical bonding is very dependent on the electrons. And if you remember from last chapter, we said that all electrons can be divided into two categories. You have the core electrons. These are the innermost electrons. They're the closest to the nucleus. They're the lowest in energy, and they tend not to be involved in chemical bonding. And then we have the valence electrons. These are the outermost electrons. They're furthest from the nucleus. They're the highest in energy, and these are the electrons that are going to be involved in chemical bonding. So all electrons are either core or valence, and it's the valence electrons that participate in chemical bonds. And primarily, the way that electrons participate in bonding is either through sharing of electrons or by transferring electrons from one atom to another. Now, the reason molecules and atoms form bonds is because it allows the molecules and atoms to lower their energy. And in general, nature prefers states of lower energy. And so that's why atoms bond. They're trying to become more stable and lower their energy. All right, so this slide is basically a review of what we learned last semester. We said that there are three basic categories of chemical bonds: ionic bonds, covalent bonds, and metallic bonds. And I have the definitions on the next slide, but what I would recommend you do is pause the video at this point and see what you remember about these types of bonds. Things you want to think about are what types of atoms would participate in an ionic bond or a covalent bond, and then what's happening to the electrons in those bond types. So pause the video for a second, see if you can come up with some definitions or descriptions of these, and then we'll talk about them on the next slide. Okay, so let's compare what I came up with what you came up with. So for ionic bonds, the types of atoms that are typically involved are metal atoms plus non-metal atoms. These involve the transfer of electrons. So the metals give up their electrons, the nonmetals accept those electrons. When that transfer of electrons happens, the metals become positive cations, the nonmetals become negative anions when they gain those electrons, and then the resulting positive and negative ions that we've created want to stick together. So that's the nature of ionic bonds. Covalent bonds are typically formed between two or more nonmetal atoms with other nonmetal atoms. And all of the nonmetals tend to want to gain more electrons, and so we tend not to get transfer electrons in this case. In covalent bonds, we think about the electrons being shared in pairs. And then the third type of bonding we don't talk a whole lot about, but it's good to review it a little bit. Metallic bonds are typically formed in pure metals and alloys. So an alloy is a mixture of different types of metal atoms. For example, brass is a combination of copper and zinc atoms. The way we describe the bonding in metallic bonds is the electron C model. So the valence electrons in the metals are not particularly tightly held by those atoms, and so they're able to move around in sort of a sea of electrons in between the metal atoms. All right, so let's delve a little bit more deeply into covalent bonds. And so this is something that I mentioned last semester. We know covalent bonds involve the sharing of electrons, but the sharing is not always equal. In the example that I would have used last semester, certainly is water. And so when the electrons aren't shared equally, we end up with what are called polar covalent bonds. We have covalent bonds, but the sharing of the electrons is unequal. And so one atom gets the electrons more than the other one. In the case of HCl, chlorine gets the electrons more often than hydrogen does. And so what happens, because we have this unequal sharing of electrons, is the chlorine end of the molecule becomes partially negative, and the hydrogen end becomes partially positive. And so the symbols I'm using here, this is the Greek letter delta. And so it's not an ionic compound. Chlorine doesn't have a full negative charge, but has a partial negative charge. And so to indicate that it's a partial negative charge and not a full negative charge, we use the Greek letter delta. So delta minus, lowercase delta, tells me that I have a partial negative charge on the chlorine, and the delta positive tells me that I have a partial positive charge on the hydrogen. And when we have this unequal sharing of electrons, the molecule is said to have a dipole moment, meaning it has a negative end or a negative pole and a positive pole, hence dipole. Okay, so the new concept, electronegativity. This is how we determine when there is going to be an unequal sharing of electrons and which atom gets more of the electrons and which atom is electron deficient. And so electronegativity is the ability of an atom in a molecule to attract the shared electrons to itself. So the greater the electronegativity, the greater the ability of that element to attract electrons. And so this is similar to two concepts that we learned last chapter, electron affinity and ionization energy. These are periodic properties. The ionization energy, for example, tells us how much energy is required to remove an electron from an atom. So the higher the ionization energy is, the harder it is to remove the electrons. And the harder it is to take away those electrons. Whereas electron affinity is the energy released when we add electrons to an atom. And so these are kind of related to how much atoms want electrons or holding on to electrons that they have. And electronegativity is similar. The trend in both electron affinity and ionization energy was that when we went up and to the right in the periodic table, these properties increased. So fluorine has a very high ionization energy and a very high electron affinity, whereas something like cesium has small ionization energies. It's easy to take its electrons away, and relatively low electron affinities. They're not particularly clamoring for more electrons. The trend in electronegativity is the same. So electronegativity also increases as we go up and to the right in the periodic table. And so fluorine is the element with the highest electronegativity. And then cesium is one of the elements with the lowest electronegativity. All right, here's a table of some actual electronegativity values and sort of see what these values tend to be. We mentioned that fluorine has the highest electronegativity, and you can see it has a value of 4.0, right? And then cesium has, at least in this chart, the lowest electronegativity along with francium, right? Down here in the bottom left, they're going to have low electronegativity values. All right, so what we can do with these electronegativities is this can tell us what type of bond is going to be formed between those two atoms. And what we do is we look at the differences in electronegativity between the two atoms that are bonded that we're considering. And so we can use this to classify our bonds into three categories. So we have what we would call pure covalent. So this is where they're basically sharing the electrons more or less equally. And so H2, Cl2, and N2 are examples of pure covalent bonds. And it would make sense, right? Hydrogen obviously is going to have the same electronegativity as another hydrogen atom, so their difference in electronegativity is 0. And so the general rule of thumb that we use is for a bond to be pure covalent, the differences in electronegativity need to be less than about 0.4. We said that polar covalent bonds are when they're sharing the electrons unequally. So still basically sharing electrons, but the sharing is not equal. And so one atom is going to get the electrons more than the other atom. And so typically when the electronegativity differences are between 0.4 and 1.8, we would classify that as a polar covalent bond. And water and hydrogen fluoride would be two examples of molecules with polar covalent bonds. If the electronegativity difference becomes great enough, right, then the electrons just aren't sharing at all, and the electrons are completely transferred from one element to another. And in this case, that would then be classified as an ionic bond. And as we would expect, two examples of ionic bonds are between lithium and fluorine, right? A metal and a non-metal. So based on what we already know about ionic bonds, we would have predicted that to be ionic. Same thing with sodium and chlorine. Metal plus a non-metal, we would expect to form an ionic bond. Now, my purpose of showing this slide is to point out, don't get too hung up on those categories and the numbers that I gave in the last slide. We want to know those and sort of use those as a rule of thumb, but nature doesn't really care how we characterize these bonds and which category we put them in, right? The atoms and the molecules are going to do what they want to do. And so in reality, the differences between pure covalent, polar covalent, and ionic, these aren't sort of black and white categories. It's more of a spectrum. So what we're showing on this slide is different compounds and the ionic character, right? So something that's 100% ionic means that the electrons have been totally transferred from one atom to another, whereas down here in the 0% means that they're sharing 100% equally. And so you can see, even for things that we would say are ionic, like they're not 100% ionic character. And then you've got something like HF, which we would probably classify as polar covalent, but right, it's sort of in between being covalent and ionic. So all I'm really saying here is that these classifications are useful. By putting these things into categories, it helps us know how we would expect them to behave, but it really is more of a spectrum rather than these three discrete categories. Okay, now I do want to get back to those categories because they are important, and so I have a couple examples here, and I want us to determine whether the bond between each pair of these atoms is pure covalent, polar covalent, or ionic. And so the first one is easy, a nitrogen plus a nitrogen. They're going to have the same electronegativity, so that's going to be pure covalent. But let's go back to that table of electronegativities and see what the numbers look like. Okay, so nitrogen and nitrogen again, right? Nitrogen, if I have two nitrogens, they have the same electronegativity, so the difference in electronegativity is going to be 0. So an N and an N, that's going to be pure covalent. Right, then we look at nitrogen and oxygen. And so nitrogen has an electronegativity of 3, oxygen has an electronegativity of 3.5. So the differences in electronegativity is 0.5, and we set our cutoff. If it's about 0.4 or less, then we'd say it's pure covalent. If it's between 0.4 and 1.8, then we would categorize it as polar covalent. So 0.5 is bigger than 0.4, so we would classify a bond between nitrogen and oxygen as polar covalent. Right, when we look at sodium and bromine, so we have sodium here with an electronegativity of 1.0, bromine is here with a 2.8, so that difference is 1.8. So we would classify that as being ionic. Now I have another one that I put down here. I'm going to go a little bit out of order. If I just gave you sodium and iodine, and I said, before we'd ever mention the concept of electronegativity, would you predict that a bond between sodium and iodine would be ionic or covalent? And hopefully you would have said ionic, because sodium is a metal, iodine is a nonmetal. That should be an ionic bond. And this kind of goes back to 2 slides ago when I said, don't get too hung up on the numbers. Right? If we look at the electronegativities of sodium and iodine, we have 1.0 for sodium, we have 2.5 for iodine, and so that's a 1.5 difference, right? Based on sort of the cutoffs that I gave a couple slides ago, to be considered ionic, it has to be 1.8 or greater, right? And so this is where this really becomes, that's more of a rule of thumb. A sodium and iodide bond is not polar covalent. That is an ionic bond, but it has more covalent character than maybe a lot of other ionic bonds. So So there's definitely some gray areas here, but don't forget what we've already learned. Right? If you've got a metal plus a nonmetal, that's probably going to be ionic. And you don't always have the electronegativities in front of you, so you want to use those, keep those old rules in mind. Don't throw that stuff out. And then the last example I have here is maybe the most important one, and that is a bond between carbon and hydrogen. So hydrogen has electronegativity of 2.1, carbon 2.5. That difference is 0.4. We said 0.4 or less is going to be pure covalent, and that is definitely the case here. Now, the reason I said this is so important is because a lot of compounds in chemistry are what we call organic compounds. They're carbon-based. And the most common other element in these organic compounds is hydrogen. And so when you only have carbons and hydrogens, you're going to have all pure covalent bonds. There's no polar covalent bonds when I just have carbons and hydrogens. So put a star by that. Carbon and hydrogen, those bonds are always purely covalent. And that's a very important concept that we're going to use over and over again. And for those of you going on to take organic, it's going to be supremely important in that course as well.